section 2.9, density. The density of a substance is the ratio of its mass to its volume. And so we've got a little equation for density. Density equals mass divided by volume, or abbreviating, we use D for density, M for mass, and capital V for volume. Density is a fundamental property of substances. Different substances have different densities. And so a piece of lead has a different density than a piece of iron or a piece of wood or a bucket of water. Each of these things has a different density. The density does not depend on the size of the sample. If you have 1 cup of water or a gallon of water, the density is the same, because it's the mass of it divided by the volume. If the mass is larger, the volume is larger also. You could think of density as sort of the heaviness. We know that sometimes you pick something up and it's much heavier than you expected. My children are very dense. My husband's very muscular, and so my kids are real solid. And so, you know, when my kids are 4, they weigh like 40 pounds. And some of my friends, their kids hit 40 pounds when they're like 7 or 8 years old, right? So other people would go to pick up one of my small children and they go, you know, it's much heavier than they expected. My children were dense. And then I go to pick up somebody else's 4-year-old and I almost throw them in the air because they only weigh 20 pounds. And my kids weighed 20 pounds when they were 4 months old, right? So density. It's the heaviness for the size. We calculate the density by taking the mass of the object and dividing by the volume. So as an example, here we have a sample of liquid. The volume is 22.5 milliliters. The mass is 27.2 grams. Calculate the density. Well, we can't do this with dimensional analysis. We actually have to use the equation. So we need to remember that density equation. The density is the mass divided by the volume. So we identify the volume is 22.5 milliliters. In this problem, it comes out and says the volume is. Other times, it might not say volume. But when we look at the unit milliliter, we should recognize that milliliter is a unit of volume. And then a mass of 27.2 grams. Gram is a unit of mass. So to calculate the density, we're going to take the mass, 27.2 grams, divide by the volume, 22.5 milliliters. You take your calculator and you do the division. My calculator has given me a big old mess of a number. 1.2088, and the 8's just go on forever, repeating. And then we look at the units. Do these units cancel out? No, they don't. So we just write them down as they are. So this is grams per milliliter. And then we have to consider significant figures. Here we have division. And the rule for division is you look at the number of sig figs in the things that you're dividing. How many significant figures in 27.2? 3. And how many in 22.5? Which is smaller, 3 or 3? 3. So our answer should have 3 sig figs, right? So we're going to round it off here in the 3rd digit. So we look at the next digit, it's an 8, so we're going to round this up and we're going to report the answer as 1.21 grams per milliliter. That can also be written 1.21 grams / milliliter. Those are the same thing. Any questions? So these end up being word problems, but they are word problems that need an equation. So we're given a mass and a volume. We're asked to find the density. Here, instead of doing dimensional analysis, we have to use an equation. Just want to talk a little bit more about density. Some of you had lab on Tuesday and some of you have lab today, and we do a little bit with density in that lab. Density determines whether things will sink or float. The density of water is about 1 gram per milliliter. And so if the density of an object is greater than 1 gram per milliliter, say like a glass marble or a chunk of metal, it's going to sink. And if the density is less, then it will float. So what do we know about wood and water? Does wood float in water? It does, right? So what can we tell about the density of wood relative to the density of water? Is wood more or less dense than water? It's less dense. Liquids can also float in each other, and we'll see that in lab. You've seen that in the kitchen too. If you put oil and water in the same container, which one goes to the top? The oil. What does that tell us about the density of the oil? It's less than the density of water. Even if there's more oil, even if the oil weighs more than the water does, it will still float on top because its mass divided by its volume will be less. So things that are less dense float in things that are more dense. Well, density is very useful as a conversion factor. So we can use it to convert between mass of an object and volume. So here's an example. For a liquid substance with a density of 1.32 grams per cubic centimeter, what volume should be measured to deliver a mass of 68.4 grams? So this is a word problem, and the strategy is to identify the numbers in here and the units and figure out what they mean. So there's 2 numbers with units given. The challenge for a problem like this is deciding which of these numbers do I start with. Here we have grams over cubic centimeters, and here we have grams. This is a simple unit, and this is a compound unit. It's got 2 units in it that are divided. If we write that out, 1.32, we can write that vertically as a fraction. Now that kind of looks like a conversion factor, doesn't it? That is a relationship between 2 different units. This is our conversion factor. So that's not what we want to start with. We want to start with this guy. So our path then is we're starting with grams, and what does it ask us to find? It asks us to find volume. So we're trying to find volume. It's not specifying the unit, but let's look at this guy. This is relating grams and cubic centimeters measure what? Volume. So since it doesn't specify the unit, we can use any volume unit we want. So let's choose to use cubic centimeters because that would be easy. And when you have a choice to make your life easier, go ahead and make it easier. Don't make things hard. So we're going to do this in one step. So we're going to start with the 68.4 grams. And we have one factor. And our path is grams to cubic centimeters. So in our equation, we write grams, and then the next one is cubic centimeters. We want to get rid of this unit, so we write it in the denominator. So it will cancel out. We put the units in first, and then we put in the numbers. The units tell us where to put the numbers in. So here's our density. 1.32 grams. Those go together, we have to keep them together. So 1.32 goes on the bottom because that's where gram is. Now, there's no number up here. That's troubling to some people. Well, if we need to write a number, what would we write? 1. For this liquid, 1 cubic centimeter weighs 1.32 grams. So now we've got everything in place. We take 68, right, calculator turned itself off, 68.4 divided by 1.32 equals, and one other interesting number, 51.81818181, repeating. And what unit is left? Centimeters cubed. So write down the whole mess your calculator gives you, write down the unit, then go back and look at the significant figures. The good thing about writing down that whole mess is if you realize later that you did your sig figs wrong, you can go back and fix them. You don't have to redo the whole calculation. So how many significant figures here? And how many here? And so how many should the answer have? 3. You'll find with a lot of the problems in the book and in the homework, it ends up being 3 significant figures. So then 51.8 cubic centimeters of this liquid are going to weigh 68.4 grams. Any questions? Density is a conversion factor. This is a table from your textbook. It gives some densities of common substances, charcoal, ethanol, ice, water, etc. We see down here platinum, a density of 21.4 grams per cubic centimeter. Platinum is very dense. It's even more dense than gold. Gold is really dense, 19.3 grams per cubic centimeter. That's almost 20 times heavier than water. Now, if you've ever lugged a big bucket of water, you know that water is pretty heavy, when you're carrying a large amount of it. Think of that amount of gold weighing 20 times more. It always cracks me up in the movies. You can always tell when they're using fake gold, right? Because you see these guys slinging around bags of gold. They wouldn't be slinging around bags of gold. Those are like, just pieces of aluminum or something, painted gold, or bricks painted gold. Gold is actually much heavier than bricks. And so, it just cracks me up. And then the cartoons are a whole nother story. Cartoons seem to be set out to just destroy all the laws of physics, right? This is crazy. So sometimes doing homework problems, they may give you a substance. They might say, well, we've got 27 grams of aluminum. What's the volume of it? And they don't give you the density. You have to go look it up in the table. You do not need to memorize this table. Okay? There is only one density that I think you should learn, and that's the density of water. And that's, one of those really tough numbers to remember. 1. The density of water is 1. And that's actually not an accident. The units of grams and cubic centimeters were defined around the density of water, so it did come out to be 1. Okay, another example. A drop of acetone, and that's the main ingredient in nail polish remover, has a mass of 35 milligrams and a density of 0.788 grams per cubic centimeter. What is its volume in cubic centimeters? Well, we've got 2 different numbers here. Oh, let's go back to yellow. So we have this guy, and we got this guy. I really need to format this better so that it doesn't break onto the next line. So the general strategy, we have to figure out what we're starting with, bless you. We have to figure out where we're ending up, and then we have to figure out how we're going to get there. Well, where we're starting with might not be obvious. What are we trying to find out? Volume in cubic centimeters. I'm going to write the path up here So cubic centimeters is what we're trying to figure out. And we have to figure out what are we starting with. Well, we've got these two numbers again. Here we've got grams per cubic centimeter, and here we've got milligrams. Anytime you have a per unit, that's probably going to be a conversion factor. So let's try starting with this. If you start with the wrong thing, and then you realize, wait, this isn't going anywhere, then just start over with the other one. So we're going to start with milligrams. And then we need to get to cubic centimeters. Can we go from milligrams to cubic centimeters in one step? No, we don't have a relationship for that. We have a relationship between grams and cubic centimeters. So if we had grams in the middle, we could get from grams to cubic centimeters. Can we convert from milligrams to grams? Yeah, we can do that. We learned how to do that. So there we have our path. It's going to have two steps. So 35 milligrams, 2 arrows in the path means 2 fractions. And the map tells Dora milligrams to grams to cubic centimeters. And so down here we've got milligrams, grams, cubic centimeters. Getting the path together is the hardest step. That's the critical point. Once you get that, everything falls into place. We're going to take milligram and put it in the denominator because we want that unit to go away. Get out of here, milligrams. They're going to cancel out. We need to get rid of grams, so we're going to put that down here. The grams cancel out. We have all the units in place. Now we can take care of numbers. We have 2 fractions here, 2 conversion factors. We might look at that one and I'm like, oh, that's that metric thing. Yeah. Let's do this one first, because this one's given. 0.788 grams per cubic centimeter. Does the 0.788 go on the top or the bottom? It goes on the bottom. 0.788. And then if we want to put a number up there, it's going to be the number 1. Now we have to go back and deal with this. What does the prefix milli mean? It means 10 to the what? 10 to the negative 3. Okay, you need to start working on memorizing those metric prefixes. So I have a gram, and those are equal, and now I have milli in the bottom. I need the numerator to equal the denominator. I need the top of the fraction to be equal to the bottom. Right now they are not. A gram is not the same as a milligram. I've got milligram down here, so I'm going to write what it means up here. So I'm going to write 10 to the minus third on the other side of the line from the prefix. I'm teaching you a pattern of using metric prefixes where you never write the number and the prefix together. There are other ways of doing it, but it's confusing enough, so we're just going to keep with one method. So that's 1 times 10 to the minus third and 1 milligram. So what I've got here is 1 and 1. Those are the same. I have gram and gram. Those are the same. I have 10 to the minus third and milli. Those don't look the same, but 10 to the minus third is what milli means. Okay? We have to learn how to do metric conversions like this. Yes?
Why wouldn't you put the negative 3 on the bottom?
That's a good question. Why not put the 10 to the minus 3 on the bottom? So 1 milligram is equal to 1, and now instead of milli, I'm going to write what milli means. It means 10 to the minus third grams. There are 1,000 milligrams in a gram. When you put milli in front of it, it makes the unit smaller. If you put something like mega or kilo in front of the unit, it makes the unit larger. So this is a 1-letter abbreviation for a factor of 10 that makes the unit bigger or smaller. Does that help at all? This is one of those things that is just hard for a lot of students to get their brains around. And if you're one of those many students that's like, I'm always putting it in the wrong place, come and talk to me. And we'll get on the whiteboard and we'll go over it until you have that aha moment. And once you see it, it'll be easy, okay? I promise you. So now we've got all of our numbers in place. We need to use the calculator. So when we get to this, the way that we enter that, let me just clear this out down here. To do that on your calculator, you're going to press 1 EE, the change sign button, whatever yours looks like, and 3. You're not going to do times 10. You're just going to use EE. Your calculator might have EXP. If you're having issues with your calculator, please come see me after class and we'll get it straightened out. Because entering numbers in scientific notation is also a critical skill. So I'm pressing 3,5 times 1 EE, that change sign button, and 3 to give me the 1 times 10 to the minus third. You can divide by 1 and multiply 1 if you like to. And then I'm going to divide by 0.788 and press equals. And this is telling me 0.044416244. And the unit that's left that I didn't cross off is cubic centimeters. Did you come up with that answer? Now we look at significant figures. How many significant figures in the number we started with? 2. Okay. And what about this factor? How many sig figs? We don't have to think about it because that's exact. It's defined that way. It's within the metric system. Just like there are exactly 12 inches in a foot, because that's what we decided, there's exactly 10 to the minus third grams in 1 milligram. And then this guy, how many sig figs? 3. So which is smaller? 2. So we're going to round to 2 significant figures. These are leading zeros. They don't count. Sometimes students want to round this off to 0 because they're counting, well, there's 1 0 and there's another 0. That's 2 significant figures. I'm rounding it to 0. No, numbers never round to 0. The first significant figure is the 4, and then the second one is the next 4. So those are the 2 digits we're keeping. We're looking at this guy. He's smaller, so we're going to round down, and this is 0.044 cubic centimeters. We could also express that in scientific notation, which makes those pesky zeros go away. It's 4.4 times 10 to the minus 2 cubic centimeters. So either of those answers is fine. Any questions? A pure gold metal bar displaces 0.82 liters of water. What's its mass in kilograms? And because this is on the PowerPoint and we don't want to have to go paging through books, I'm giving you the density of gold, 19.3 grams per cubic centimeter. So we need to make a path. What are we trying to find out? The mass in what unit? Kilograms. And so we've got 2 numbers here. We've got 0.82 liters and we've got this density. Which is the one we're starting with? The 0.82 liters. Because this looks like a conversion factor, and it is. Well, how do we get from liters to kilograms? This one's a little more complicated. We're probably going to have to use this, right? This is grams and cubic centimeters, but neither of those units is the beginning or the end. Grams, though, and kilograms, that's one of those metric conversions, right? So if we got grams, we could get to kilograms. Now this unit is in the density. The density allows us to convert between grams and cubic centimeters. So if we got cubic centimeters, we could get to grams using the density, right? Liters and cubic centimeters.
So a cubic centimeter is a milliliter.
A cubic centimeter is a milliliter. 1 cubic centimeter is exactly the same as 1 milliliter. That is a relationship that is often forgotten by beginning students. So I didn't really leave enough space in here, but so if we knew milliliters, we could get to centimeters. And then could we convert from liters to milliliters? Oh yeah, we could do that. So there's our path. Sometimes coming up with the path requires a little bit of thinking. It's not always obvious. Okay, so let's write this out. 0.82 liters. How many arrows in that path? 4, right? So there's going to be 4 fractions. And the path is liters to milliliters to cubic centimeters to grams to kilograms. Dora's going to have to chant that several times to remember it, but we've got it written down. Liters to milliliters to cubic centimeters to grams to kilograms. Once we've got the path written out, we just follow it. Then we're going to put units in the denominator so that they all cancel out, and all we've got left is this guy at the end. So we're going to take liter and put it down here. So those cancel. And then we put milliliter down here. So those cancel. And cubic centimeters down there. And grams down here. After we have all the units in place, then we stick in numbers. You can put the numbers in. You can pick any of those fractions that you want. Whichever one is easiest is what I always like to start with. So this one might be the easiest because it's actually written out here in the problem. 19.3 grams per cubic centimeter. So we need to put the 19.3 with the grams, and then that will be 1 cubic centimeter on the bottom. What's the other one that we've got written out? This one, right? So 1 cubic centimeter is the same as 1 milliliter. So that was easy. The first one and the last one are using the metric prefixes. So let's do this one. We just did one with milli, but it was milligrams. Was it milligrams? Yeah, it was milligrams. So milli means 10 to the minus 3. So I'm going to put 10 to the minus 3, not up here with the m, but down here. Another way to think of this is milli is like a nickname for this number. My third son's name is Thomas Calagoa. We never call him that, not even when he's in trouble. He's always Tommy. That's his nickname. So you can think of the leader here as the last name. And so this is Thomas Calagoa, and this is Tommy Calagoa. Does anyone call him Thomas Tommy Calagoa? No. You don't use your full name and your nickname together, one or the other. And so that's how it is in these conversion factors. You can have the prefix or the number, but don't put them together. Okay? The number goes on the other side of the line from the prefix. So 1 milliliter, 1 times 10 to the minus 3rd liters. So then going over here to the end, here we have a prefix again, kilo. Kilo means 10 to the what? 10 to the third. Where am I going to put 10 to the third? On the top with kilo or on the bottom? On the bottom. I don't want to put it with its abbreviation. That's putting the full name and the nickname together, and we don't want to do that. 1 kilogram, 1 times 10 to the third grams. Any questions? Now we do the math. So 0.82 times the top, divide by the bottom. So this time I'll do the ones. Times 1 divided by 1 EE, change sign 3. Then it would be times 1 divided by 1 times 19.3 divided by 1 times 1 divided by 1 EE3 equals. And I'm coming up with a number of 15.826. And the unit that's left that's not crossed off is kilograms. Anybody else get that number? Did the math, wrote down the number. Now we have to look at significant figures. How many in this first number? 2. That 0 at the beginning doesn't count. How many in this one? Exact. How many in this one? This is exact also. How many in this one? 3. 19.3. There's 3 digits there. And how many in the last one? That's also exact. So we've got 2 in our starting number and 3 here, and all the rest of them have infinite number of sig figs. So then our answer should be rounded to 2 sig figs, and so we're going to call this 16 kilograms. Any questions? So I'm going to skip those two. I'm going to talk about this orbiter. Back in 1999, NASA lost a $94 million orbiter because 2 groups of engineers didn't communicate about their units. One was using inches, one was using centimeters. As a result, the calculations were wrong, and the orbiter was orbiting in a way that caused it to descend too far into the atmosphere, and it burned up. $94 million gone over units. Units matter. Sometimes students are like, well, yeah, I got the number right, it's just the units wrong. Well, details matter. Details don't always matter, but sometimes they do, and we need to recognize when they do. If you're trying to log into your bank account online so you can pay a bill, does it matter if you get your password exactly right? Yes, it does. If you're trying to email your professor to get a letter of recommendation for a scholarship, does it matter if you type the email address in exactly right? It does. There are things in life where it has to be exactly right. So don't complain about that to me, please. So what happened was that the Mars orbiter was supposed to have an orbit at 155 kilometers. And so one group wrote that as 1.55 times 10 to the 5th meters. And the second group of engineers programmed it for 1.55 times 10 to the 5th feet. Feet, meters, they're just measures of length, right? Yeah. So the question here is, what was the difference in kilometers between those 2 altitudes? Well, how many kilometers is this? Well, You're thinking, that's not really obvious to me. Well, let's do it like this. 1.55 times 10 to the 5th meters, and I want to make that into kilometers. I'm going to put the units in like this. I'm going to multiply by kilometers, the unit I'm trying to get to. I'm going to divide by meters. And kilo means what? 10 to the 3rd. So 1 kilometer is 1 times 10 to the 3rd. And so this ends up being 1.55 times 10 to the 2 kilometers. So 155 kilometers. That's what the orbit was supposed to be. So 1.55 times 10 to the 5th feet. Okay, so there's multiple ways to do that conversion. I'm going to go with stuff that I know. 1.55 times 10 to the 5th feet. Well, I know the relationship between feet and inches. So I'm going to go to inches. And then I know the relationship between centimeters and inches. And then I can go to meters. And then I can go to kilometers. You might think, well, that's an awful long way. But I know those conversion factors in my head. And so if I don't have access to other stuff, I'm going to go with what I know, even if it's a little bit tedious. So I'm going to put feet down here, inches down here, centimeters down here, and meters down there. How many inches in a foot? 12. So 12 inches is equal to 1 foot. What's the relationship between centimeters and inches? 2.54 centimeters is 1 inch. That's a really helpful one to know. What does centi mean?
100.
It means 1/100th, which is 10 to the minus 2. So centi is on the bottom. I'm going to stick what it means on the top. 10 to the minus 2. And then kilo. We just did one with kilo. Kilo means 10 to the 3rd. I don't want to put 10 to the 3rd with the K. I want to put it on the other side. So 1 kilometer is 1 times 10 to the 3rd meters. 1.55 EE5 times 12 times 2.54 times 1 EE, change sign 2, divided by 1 EE3 equals bless you, 47.244 kilometers. If we're going to round that with significant figures, we're going to get 47.2. So it was supposed to orbit at 155 kilometers. It actually orbited at 47.2. That's a bit of a difference, isn't it? So this number down here answers the second question, how low did the probe go? It was orbiting at 47.2. The first one, what's the difference in kilometers between the two altitudes? Well, 155 minus 47.2, 107.8 kilometers. How big is a kilometer? It's on the order of a mile. So the relationship is 1.6. So personally, I have a hard time remembering which is longer. Is it 1.6 kilometers to the mile or 1.6 miles to the kilometer? I have a hard time remembering that. But they're ballpark the same size, right? So the difference here was on the order of 100 miles. That's a big difference when you're talking about orbiting the Earth, right? 100 miles too low, the force of gravity is too great and it just pulled that thing in. End of chapter 2. So at the end of these slides is the chapter in review. And these topics are also listed at the end of your chapter in your textbook. So if you're asking me for a study guide, these are the things you should be studying. Chemical skills, these are things you should be able to do. You should be able to report measured quantities to the right number of significant digits. You should be able to round numbers. You should do sig figs with these different calculations. You should be able to do unit conversions and use density as a conversion factor.